Well, hello. Thanks for spending your precious conference time with me, learning about how Capital One's security organization found a way to use Delta and Databricks to power a scale backend for our interactive security event analysis application, or for the security folks, our SIEM's UI, right? My name's Scott Shankine. I'm currently a distinguished engineer at Capital One. I'm the lead engineer for our cybersecurity organization, and I sponsor a lot of work that we do across the enterprise for advancing data engineering causes. That's sort of how I got involved with all this, right? For most of my career, I've been very heavily attracted to systems optimization problems, and I've always had a bit of an obsession trying to get like the last little bit out of every compute workload possible and get stuff for the cheapest way possible. So. That's how I came to be part of the agenda that we'll talk about today. All right, so in today's talk, we're going to discuss some trade-offs that I think most of us generally make around scale, cost, and performance when working in a lakehouse architecture. Then we'll pivot to talk a bit about Capital One's journey to adopt a lakehouse architecture, along with some of the limitations that we encountered. And then we'll talk about how we overcame those limitations, which is the interesting part of the talk, and do a deeper dive into the technical inner workings that allowed us to achieve some pretty improbable goals. All right, so my first introduction to our cyber lake ecosystem was in a call with our finance team, of all people, right? Our cyber data system was one of the most expensive applications in the company, and we were operating way outside of our finance team's assumptions for spend, right? The team of security experts that had built our system felt that these very high costs were justified and necessary, given that we had requirements to satisfy around high productivity for our investigators, very fast access, and to have data that was ready to consume in case we needed to do like a deep look back or a retrospective analysis of old data, should we have an incident or something similar. So it was like big and expensive, the system. I started to think about a system of trade-offs in data that is very similar to the triple constraint that you hear about like in project management. And in this triple constraint, the axes are high performance, scale, relatively low cost, and among those, generally speaking, you can only have two. And I let this become a bit of a crutch for myself, and I've observed fairly ubiquitously, like throughout the industry, this is how people approach the problem. They like sort of take it for granted that they can't get all three. So about 6 years into my connection to Capital One's cyber data ecosystem, I came to meet a friend who had a very similar professional focus to mine. And he chatted to me about how much lift his security organization got from adopting the Delta Lake ecosystem, right? For Databricks and Delta, they solved for very inexpensive data at scale, and they consolidated streaming, batch, interactive warehousing, all using a single data source. And at the time, we were using numerous technologies to do the same. And we had less capabilities than they did. And I always have my hat on, like I'm in this forever quest to try to make my system simpler and less expensive. So after a ton of prototyping, I personally got convinced that this was the right approach for my team. And we chartered work to consolidate to a lakehouse architecture using Spark, Delta, Databricks. We found that we could replace a meaningful portion of our infrastructure using a single inexpensive copy of data, right, the Lakehouse Promise, which provided really a lot more capability than the litany of more specialized cybersecurity tools that we were using up to that point. And this system had, in that triple constraint, it was big and it was cheap, right? And it was really a great transition for our team. It's like, it's a little bit too much to talk about in a lightning talk, but I'll leave it at, it was the right architecture decision for us, and it was one of the best system investments I've ever been part of. But there's a complication to all this. Though we'd driven a lot of convergence around Delta and around our single copy of data, we still had a separate system, a separate copy of our data, a separate load process for our fast, interactive data use cases. right? And this system was fast and big, right? Remember, fast, big, cheap, you get two, but definitely not cheap. Our analysts were still using this very expensive search engine. You can probably, if you're a cyber person, figure out what I'm talking about, to retrieve and pivot through our data. And this was costly from infrastructure standpoint, licenses were expensive, and most importantly to me, there was a huge draw on our human component, right? Like our resources were spending a lot of time doing duplicative work that generally just didn't feel good. So I challenged myself and my team to try to figure out if there was a way that we could break through the triple constraint and serve fast scale use cases using all of the relatively inexpensive tools that we got from the Lakehouse architecture and from Delta and Databricks. The paved paths, so to speak, for making the Lakehouse work at scale for low latency interactive use cases weren't particularly great. One option you have is to use gigantic Spark clusters. If you have enough data and it's big enough, you can essentially throw hardware at the problem and indefinitely parallelize your work until you get the performance that you need. And while this is a lot less moving parts and it was less of a burden on the people on my team, it really wasn't any more cost effective than having an actual search engine. Second option would be doing something a little more creative, like hyper-segmenting your data. Think about like maybe a table for every person in the organization or every server. And again, this is not a great option given the enormous support burden and the design and technical complexity that's involved. Imagine hundreds of thousands of tables. It'd be very difficult to maintain. So clearly the conventional thinking around this problem wasn't going to get us to that goal of having fast, big, and cheap, right? All using one very simple set of systems. So to move forward, we had to get a much deeper understanding of the fundamental problem that we were solving, number one. And number two, we needed to understand the technology that we're using much more deeply than the way that people in the industry generally learn about how Delta and Databricks and Spark worked. So our first order of business was to get a much deeper understanding of what our users were actually doing, right? The people in our security operations center, they didn't work at random, so there had to be some sort of pattern as to what they were doing. And patterns are generally very useful in computing and in data problems. So the first thing we noted was that nearly every query that our users ran during an investigation revolved around some sort of subject, right? Like a noun. Think of cybersecurity subjects being things like people, hosts, cloud accounts, networks, appliances, and so forth, right? These are high cardinality things, which we'll look at much more deeply in a few minutes, but you can think, if you're not familiar with it, high cardinality is being something you have a lot of. Like at Capital One, we have thousands of employees, and we have hundreds of thousands of hosts, or even millions of hosts if we look at a long enough time frame. The second thing that we noted was that our users generally were working in a relatively small time frame. So while we had petabytes and months of data, the active portion that most people were working on was actually pretty small. And as an added bonus, a day's investigations, we were typically looking at something that happened like, an hour ago. And so they were all like looking at the same small window. These time frames, like hours and days, for those who haven't heard these words before, they're low cardinality, meaning like you have a relatively small number of them. We have millions of servers, tens of thousands of users, but we don't have but so many days or hours, right? And these low cardinality fields are extremely useful for zooming into a very large data set. And we'll see a lot of detail about like how you can think about that and visualize the actual data that underpins. All right, so bringing together these ideas of a consistency of query pattern, which I think applies to far beyond cybersecurity, right? Like anything that deals with high human productivity, like call centers, right? Customer servicing, fraud investigations. We're able to leverage some basic capabilities in the Delta stack to make things faster, right? So the first thing that we're going to talk about is data skipping. And you've probably seen like in Spark UI, something that talks about data skipping and some things in documentation. We're going to go pretty deep. Data skipping is one of the simplest, truly, in my experience, most poorly understood parts of open table technology. Skipping will allow a query engine like Spark to eliminate unnecessary work, completely skipping the processing in question, right? So if you can prove that a set of files definitely isn't part of your investigation, you don't have to process them, and you don't have to spend the time doing that. But most of our data in the wild gets ordered organically based on the order that it came in from a source. And in these cases, you would only get effective skipping by accident. And generally, you will get a lift from like this accidental organic sort of skipping, but it kind of looks like the picture in the slide, right? Like 15-ish%. Marked, but not enough to like get us to super high performance search engine sort of speeds. Fortunately, the insights that we talked about before would allow us to lay out our files and co-locate our data in a way that data that's likely to be queried together is very proximate, very close. In our cases, again, among time frames and subject. And so we can force our files into a format that'll allow Spark to skip the vast majority of potential files and compute work and really shave off a huge amount of time. So you look at the diagram, you can see like the difference between an organically laid out data set and a well laid out data set. And you imagine that if you're only processing 2 files, it's less work, it's less time, it's much faster. And we'll dig much deeper technically into how that works in a moment. So relaying out our files using delta optimization techniques reduced our query latency from hours or minutes to a few seconds, but it's still too slow. An interactive application has to be 2 seconds or less, or a human user will perceive very poor performance. So capitalizing on the fact that most of our users would be doing investigations around a generally similar time frame, using data caching became a very attractive option for accelerating workloads. Fortunately, in Databricks, not an open source Spark, but in Databricks, they have a feature called DBFS cache that will short circuit some of the most expensive data operations, like pulling files remotely from S3 or something similar. And it stores it locally on NVMe storage on the server that's actually going to read the file. And this took another few seconds off our average query. And we're getting pretty close, but it's still too slow for our very finicky requirements from our users. So finally, as a Databricks user, you're probably familiar with this concept of photon acceleration. And most people think, like, I turn on photon, it goes faster. There's a little more to it than that, though. So photon does a couple of very critical things which close the last part of our performance gap. First, photon will aggressively prefetch data that you're running in your query so that it ends up in that fast NVMe storage on your server before the server even tries to access it. And so, like, essentially zero latency. And secondly, photon employs some very interesting techniques to shortcut processing activities for files that couldn't be skipped entirely, often eliminating entire files after only downloading a small fragment, right? So more in each of these things cumulatively adds performance. Once we implemented all 3 of these techniques, we found that query times came down to just a couple of seconds, which was our goal. This meant that we were getting essentially the same performance from Delta and Databricks as from our very expensive bespoke search engine, leveraging just the same data, the same copy that we were using for data warehouse, batch processing, and streaming. So you imagine, less is better, less work, it's cheaper. So our last hurdle was to figure out how to get these very quick runtimes surfaced for an interactive web application rather than in a Databricks notebook. And fortunately, at the time, there was a new technology called Spark Connect that is a little more ubiquitous now. But it allows you to run a Spark driver in a process that's external to your Databricks cluster. Databricks releases their own optimized versions that they call Databricks Connect. But we can use this technology to embed in an API implementation, and it exposes those petabytes and petabytes of tables for us through a RESTful interface that we can consume from application front ends, right? So we have this very fast thing wired into a web application. When I saw the results, I was very, very skeptical, right? Like, no one talks about Delta at massive scale with hundreds of petabytes of data being a couple seconds. So I was positive that I messed something up in my tests. Ran them over and over again, got the exact same results every time. So in order to get comfortable that these performance results were real, I had to really understand what was happening under the covers in our Lakehouse implementation. So we'll spend our last few minutes doing a whirlwind tour of the internals of the stack. All right, so the Delta log is the foundation, or a log is the foundation of all open table formats, whether it's Delta, Iceberg, Hootie, everybody has a transaction log. You've probably seen the Delta log directory in your own structure. You may or may not know what it really does. But in very simple terms, you can think of it as a set of operations, add a file, replace a file, and so forth, that can be replayed during query execution to know what to read in the table and how to interpret the results. Since stark contrast to the traditional way of listing files in a remote S3 bucket or something, the Delta log gives you an index of pointers that tell Spark in very concrete terms what to do to traverse a set of data. And the result is better cacheability and most importantly, space to provide performance hints. And this is how foundationally this solution works. So if you were to crack open some of the files that live in the Delta log, they would look like what you see on the screen, right? So this is a sample of an add operation, like somebody wrote a file, and then there's some summary information about the file, like what partition is it part of, what range of values are contained in that file, right? So in this file, you can see it contains min-max Abel to Sally, right? So alphabetically, it contains values and first name from Abel to Sally. So if your where clause had Zachary in it or Xander, the query planner could just eliminate file name 1.parquet and just not do that work. And these skipping operations, again, account for the majority of our acceleration. As mentioned before, data's natural ordering in Parquet files rarely provides super efficient skipping. So in this example, you see 3 Parquet files, each of which contains a range of values. And so when the where clause looks for 7, it has to read everything. But with optimization and rewriting, we can compact everything toward like 2 common values. And so in order to get 7, you only have to look at 1 file, and it's 1/3 as much work in this example. Rewriting files in a read path optimized way, you have a few practical options. We don't have a lot of time to go into the details, but generally there's 3 options available. One is what we use. It's the original Delta clustering technology called Z-ordering, where you provide those high and low cardinality fields, and it rewrites your files without changing the contents of the table, right? It's all conveniently available through a SQL interface. Second option is liquid clustering, which you've probably heard a bunch about this week. And this is a little bit more flexible. It's newer. I wasn't able to get exactly the same performance out of it, but this is where most of the investment is in the stack today, and it's getting better over time. And so it's definitely worth spending some time investigating whether it's right for your use case. And then finally, you can like sort your files and write them manually. And I don't recommend this in most cases because like there's all sorts of problems that you have to deal with around like consistency of table data over time and so forth. But it's available, right? And like it sort of demonstrates that that's how the files are getting ordered and compacted. Okay, so recall high and low cardinality, which provide coarse and fine grain elimination of files. So here you see a scan job that has bad skipping, and it scans and hits everything. It's very lengthy and slow. So here we use high cardinality fields only, and you notice it's a very small number of files. And this sort of takes away the option that you have of somewhat scaling your Spark cluster out because there isn't enough work to do. There isn't enough work to parallelize. And so you're robbing yourself of like some of your last mile performance. But if you go by a high cardinality and a low cardinality field, you get a relatively small number of files, but potentially enough files to scale across a medium-sized Spark cluster. And so this, for us, is sort of the happy medium for performance. All right, so when range-based skipping can't eliminate a file, Photon comes to the rescue, right? First, there's the proactive file elimination that we talked about, right? So Photon can look into the physical encoding of a Parquet file and make some shortcuts to figure out that like, oh, although this is in range, I don't see the value Marty in this file, so we can just skip the rest of the file. And that takes off a huge amount of time. Secondly, there's a concept in Spark called predicate pushdown, where the where clause gets enforced when Spark is reading files, not actually in the Spark engine. And so it saves copying data into memory for later processing. And that saves a ton of time. And so in Photon, there's a much more robust implementation of predicate pushdown. And so you get way less rows for Spark to actually deal with. And then finally, Photon uses CPU instructions that can process many pieces of data at once. It's very similar to how like a GPU works for an ML workload. And so this makes it so you can do like hundreds of comparisons in one CPU cycle. And so for the few rows that are left after all these things happen, it's highly parallel using just the same hardware that you have in your data center, just part of the Intel or the ARM instruction set. All right, caching is the last of our accelerants. And this is where Databricks stores fragments of Parquet files that underlie your physical tables, again, on fast storage on NVMe on your servers. And again, this is particularly effective when Databricks prefetches files. And so less network time means better performance. And it's very easy to enable. Just choose an instance type when you're provisioning a cluster. That's denoted as Delta Cache accelerated. And so that's all instance types generally that have instance store or NVMe storage. So when you combine all four of these techniques, you go from, in this case, we had like a 250-second query that went down to 0.46 seconds. Right, so like a 400x increase in performance. A lot of the stuff you see with liquid clustering, let's say you get a 10x. If you're very careful and thoughtful about your high and low cardinality fields, you can actually get down into tiny fractions of a second like we've done. All right, so putting all these building blocks together made it possible for us to build this vastly simplified infrastructure using low cost and low complexity components. And we got, I think, is great performance, 0.46 seconds instead of 250. And I feel like we've effectively defied that triple constraint. So maybe that's not a real thing, right? Our final architecture looks like this, kind of like the challenge slide. It's simple, it's easy, it's cost effective, it's highly performant, and everything's built around just a single copy of data, right, that we can use for warehousing, batch streaming, and fast interactive access. No OLTP databases, no copies of anything. And this is what, for the most part, we have in production today. So I'm really proud of that. All right. So just a quick recap. Today we demonstrated that very fast, inexpensive application data access is possible with Delta and Databricks. It's accomplished using data skipping enhancement through clustering, caching, and platform native processing accelerators. All right. Please complete your surveys, and thank you for spending time with me today. I don't know if there's people in this room after this, but I'm happy to stick after and answer some questions.